Where's Ivan? Ivan. Yeah, how'd it go? Tell me. The rectangle's area grows at a, what'd you think? Constant rate, good. Of what? 4. What do you guys think? Yeah, so you could say rate of change, but I like constant rate because this is a constant rate. So constant rate of change, ROC, of 4 with respect to length. Okay, here's the thing. So let's see if we've got it yet. What does that mean if it grows at a constant rate of change of 4 with respect to length? Ivan, you want to try? Still not sure about that. Okay, so yep, this is our journey. We're going to learn this by the end of the semester, but hopefully sooner. Evelyn, what do you think?
For every change in x, the length increases by 4.
Okay, she said for every change in x. For every change in x, what happens?
The length increases by 4.
The length increases by 4. What do we think? Agree with that? Okay. The area increases. For any change in x, the area increases by 4. Agree with that? So whether I change x a little bit or I change x a lot, the area increases by 4. Is that right? What were you going to say? For x. For any change in x, the length increases by 4x. Getting closer. Yeah.
For every change in the rectangle's length, the area is 4 times. The change in the area is 4 times greater.
Okay, for every change in x, the resulting change in area is what? Resulting change in area is 4 times. 4 times what? That change in x that you picked. And then we have a formula for that. What is that formula? I.e., what embodies that principle of this constant rate of change of 4? Yes, ma'am. dA equals 4 dx. This is what it means that the rate of change of area is 4. It means if you you can make any change to x, the resulting change in area that you'll get, dA, is 4 times that change in x that you picked. So we're going to get it. So just before I started talking, how many people had that exactly or something really close to that? Okay, about half, good. Okay, so the rest of you, so we're just, each time we practice, it gets a little more solidified. Understand it a little bit better. Any questions on this one? Yes, please.
Just to clarify.
Yeah.
Using the word, the change is 4 times bigger or 4 times increasing.
Yeah.
That would be wrong, though, right? Because it would make more sense to say change rather than assume that it's always going to be increasing by 4. Does that make sense?
So was that like you're questioning a verbal thing that was said?
No, I just want to know if it's always the change will always be increasing. Because let's say the change in x goes backwards or something, the change would still be by 4, but it doesn't mean it's always going to be increasing.
Yeah, but so then if your change in x was like say from 8 to 7 or 8 to 7.5 or something, then that dx would be a negative. And when you multiply 4 by that change in x, then you get a negative dA, which is a reduction in area. So it still works. Yeah, okay, good question. Other questions? Okay, next one. All right, so this one now. Let's see, somebody new. Here we go. Where's Ethan? Ethan Clark. Ethan, how'd it go? So this one.
So the rate grows at a constant rate.
At a, what'd you say? Did you say constant rate? Okay, so it's a changing rate. So you say changing rate. Good. That's fine. Of, and what is the changing rate of change? F of x. Good. Okay, now that we did the practice the definition on the one before, let's regroup And so if you need to, change what you wrote on this next part. Take a second to alter what you wrote. See if you can get more accurate based on what we just said about the previous one. So take a couple of seconds. What does it mean that the changing rate of change of area is f of x? What does that mean? I'll give you a hint there. So it's the model is the same as the previous one we talked about, but there is a difference. There's a little something that's a little bit different on this one, but overall it's the same principle. Where's Arpita? Arpita, did you get it?
I have written it down, but
Oh yeah, okay.
for any variation in length,
Okay.
corresponding variation in area is f of x times the variation in length.
For any variation in, so there's different lengths here. So which length do you mean? Which length for any variation in? Because like, just want to be precise. Because this is a length here, right? This is a length here.
So x.
X, right? So that any variation in x, okay?
The corresponding variation in area
Good.
is f of x times the variation in x.
Excellent. Corresponding variation in area is f of x times dx. What do we think? Okay, perfect. So this follows our rate of change definition perfectly, but there's something we've got to do a little bit differently here. This doesn't quite work. Is this true for any variation in x? So here's f of x right here, right? It's that length right there. So if I take a variation of x of, say, this much, is the change in area that I'm going to get, is it going to be f of x times dx? Will that be too small or too big? You see that'll be too small? If I hold on to that f of x and make it for the whole change in x, I'm not going to get enough area. So how do we have to qualify this? Now that f is changing, right? So the point is, if the rate of change is not constant, if it's a changing rate, then we have to put a qualification on this definition. James knows. Tell me your name again. Tia knows. Anybody in the back? How do we have to kind of put a qualification on this so that this still holds? Yeah.
So you want to state that you're adding up all values of x f of x over the interval of x to delta x.
Okay, so you're saying you want to do a sum of f times dx, okay? And what about those dx's to make that work? Yeah, so James and Tia got it. So James, what is it? Yeah, so in order for this to work, that dx has to be really small, so that we can assume, without much error, we can assume that the rate is constant over a small interval. Because as soon as dx becomes not small, then we're going to have a rectangle that doesn't match the area that's formed by the top of that curve. So for any, what? We need to say small. For any small variation in x, the corresponding variation area is f of x times dx. So with constant rate of change, big or small, doesn't matter, because your rate just stays the same. So a big change is okay, right? But if the rate is changing, this dy equals mdx is only going to work for a really small dx, because if you make it big, then your rate has changed already. Doesn't make sense. Really important concept. Okay, so let's look at. Anybody have a question on this review? Let's look at this here. So here I have a function, and I'm interested in what's happening from x equals 1 on. I have some questions for you. I want to know exactly where, this is a visual answer or a geometric answer. Where's the area of the region accumulating? What is the rate of change of the accumulating area? And what is the connection? What is the connection between the answers to number 1 and 2 above? Important questions. Again, this is kind of a review from last time. Where's the area of the region accumulating? What is the rate of change of the accumulating area? And what's the connection between your answers to 1 and 2? How do those work? Make the link. Make the link. Go. Talk.
Yeah, or no, it's accumulating from 1 to 2 because that's a function. The rate of change of the area.
And what I mean, number 1 means like at any given moment, right? So like if I were to pause it, okay, looking at the region that you have right now, where is the accumulation occurring? Okay, same thing if I were to pause it right here. This green region, where's the accumulation occurring? Go, keep talking. Okay, let's see what you talked about. Here we go. Where's Marina? Marina, so we're looking at the region at any given moment. Where is it accumulating? Where's the accumulation happening? What's that? To the right. So if I were to pause it here at any moment, I were to pause it. Where's the accumulation happening? Where in that region is the accumulation happening? Yeah, tell me, Adam. On the right edge, at X, right? That's what she said. At the right edge, at X. Okay, and what is the rate of change? F of X. Which means for any small change in X, the change in area will be what? F of X times that small change in X. We just covered that, right? Okay, so it's accumulating on the right, and the rate of change of F of X, so what's the connection between those two? What's the connection between those two? That it's accumulating on the right, and the rate of change is F of X. Just volunteer. Somebody new. What's the connection? Nobody? Where do you see F of X in this picture? How could you put something on this picture to denote F of X? What would you label on this picture to say this is what F of X means in the picture? Oh, somebody knows that. Yeah? Was that about a hand? Almost a hand? Yeah. Right, the height of the right edge, exactly. So right here, that's F of X. So what we say? We say, where is it accumulating? On the right edge. What's the rate of change? The height of the right edge, F of X. Okay? So the amount of accumulation that occurs, right, or the rate at which accumulation is occurring, is the length of the edge. The rate of change of area is the length of the edge where the area is accumulating. That length at the right side, and that's the value of the function. Super important. You see that, right? So whatever that length of that edge is, where it's accumulating, that value is the rate of change. Okay, let's go even more general now. So this will generally the rate of change for a geometric application. It's the magnitude of the boundary where the quantity is accumulating. Do you see that? What's the boundary where it's accumulating? It's the right edge. What's the magnitude of that? It's the length of it. Maybe I need to make this bigger. This is going to come back. Even when we're done with area, we're going to see it again. If I could highlight it, maybe. The rate of change in these geometric applications, area, volume, surface area, arc length. The rate of change is the magnitude of the boundary at the place where that boundary where the quantity is accumulating. So for area, what is that? That's the right edge. The right edge is the boundary where it's accumulating, and so the length of that right edge is the rate of change. But we'll see this, what I've highlighted there, we'll see it again for different geometric applications. Any questions? Okay, so let's, oh, please, please. Yeah. Yeah. So if I were to turn it on, if I were to push play, where is it going to grow? Where did it grow? Where? On the right. Do you see that? So anytime I pause this and turn it back on, it's going to grow on the right. It's growing at the right side. As long as x is increasing, which is our convention, right? So I could make x decrease, and then we could talk about that, but we usually don't, okay? So this is enough challenge as it is. So yeah, so x will always increase, and then that region will always grow on the right side. And what is that? That's x, and so that height or that length of that edge is f of x, and that's the rate of change, which we developed on Friday. Does it answer it? Okay, cool. Yes, please.
If you were to be looking between 2 and 3, so that f of x was negative.
I think I'm about to answer your question. We're going to talk about that next. Yes, thank you. Yes, just hold that thought. Okay, so let's look at, so I want you to, I got this function here. Capital F of x is the integral from 1 to x of f of t dt. I want you to elaborate on what that function is all about. What does that function mean? What is it all about? What is its function? What does it do? Tell the person next to you. Where's Becca? Becca Ario. Is Becca here? How about Andrew? Asteel, Andrew. Tell me, so what kind of function is this that we've talked about? Good. All right. So this is it's a net change function, or a net, what do we call these? Net accumulation, which is change, which is amount of change since when? Right. So this is the net accumulation of from 1 to x, but of what quantity? Area, because why area? Because little f is rate of change of area, right? Remember that? If you take the integral of a function, that function is the rate of change of the quantity that you're accumulating. So since f of t is the rate of change of area, this is a net accumulation of area function. So what was your name? You were about to ask a question? Yeah.
Yes, sir.
Sarah. Okay, Sarah was about to ask, so what about past 2 when that function, our rate of change, is negative? So over here, isn't the rate of change negative? Little f? So what is that going to do to the accumulation for values of x when our rate of change is negative? What's going to happen to our accumulation function as we increase? Accumulation will decrease because it's a negative rate, right? It's going to decrease because it's a negative rate. So is this function then accumulating area? Is it really accumulating area? So what's happening to the accumulation function now? Increasing. What about now? Still increasing. Still increasing. What's happening to the accumulation function now? Decreasing. Is the area decreasing? Are we getting less area? So area is always positive. The area is always increasing. First it's green, and then it's gray, but the size of the region, the area is always increasing. But what does our function do? Does our function do that? Does it always increase? No, when it gets to 2, you told me that function starts decreasing by how much? It starts like subtracting off this amount of area. So by the end, what do you suppose the value of the function is here at 3? Positive, 0, or negative? By the time, so if I put capital F of 3, would you suspect that that's positive, negative, or 0? Negative. Why? The gray region is bigger than the green region. By the time you get to 3, you've decreased more than you increased on the green part. Do you see that? So capital F of 3 is going to be less than 0. So this function, all along we've been saying area, it's not really area. Okay, it's certainly highly related to area, but we need to qualify that. And what we're going to do is call it signed area, meaning it can decrease. It could be negative, depending on parts of the function that are carved out below the x-axis when the rate is negative. When the function values are negative and the rate is negative, this function is going to decrease by that amount of area. So somewhere here, what happens? Somewhere right about, if I can get there, no, not fast enough. Somewhere along the way here, what's going to happen? That value of that capital F function, the signed area, is going to be maybe, I don't know, maybe here? I'm trying to guess where that capital F function is going to return to 0, because for the green regions, it's going to increase a certain amount, and then the gray is going to kick in, the negative rate, and it's going to start to decrease. And at some point, that amount of gray is going to be equal to the amount of green, and our capital F function is going to be back at 0. Do you see that? And then after that, the capital F function will be less than 0 and getting more negative. Are you following this? So this, if you just take the value of the function and make a net accumulation function, what you get is what we call signed area, which has the possibility of being of decreasing, and then of being negative also. If your function ever goes below the x-axis. Okay, so then area, just to define terms, area is equivalent to unsigned area. If you ever see area or unsigned area, this is these are equivalent. Area and unsigned area are equivalent, and they both mean the size of the region, regardless of the rate being negative or above or below the x-axis. Area is always positive. It's how big a region is. And so then we'll just use the term unsigned area to mean area. Signed area is what you get if you just simply set up a net accumulation function of, say, f, and now you're allowing for that to decrease or be negative whenever that function goes below the x-axis. So another way to say signed area is like difference of areas, right? It's like all the area above the x-axis minus all the area below the x-axis. So signed area is like difference of areas, or net area. Okay, so let me just give you a little puzzle here. See if you... So I've got two quantities here, P and Q. I want you to observe the values of P and Q as X increases and determine what exactly P and Q are and maybe set up a relationship between them. Okay? So N is the current value of X. Okay? N is the current value of X. You can see that down here. So then this is like, what's P of X and what's Q of X representing? And maybe can you set up a relationship between the two? See if you can do that. Take a minute. How'd it go? Yeah? And okay, and what's another way to say P of N then? What about the accumulation? So P of X is the same as, you could write it's the same as what? F of X, right? Isn't P of X F of X? And what is that? The rate of change of area? Not area, rate of change of? It's not the rate of change of area. It's the rate of change of signed area, because F can be negative. It's negative right now, right? So P of X, which is the same of F of X, which is the same as the rate of change of signed area, which is the length of the leading edge, right? It's the length of the right edge where the area is accumulating. Okay? Let's see. Who was I talking to? All right. How'd you do it? What about Q of X? Of what quantity? Signed area. Right. So Q of X is showing signed area because what? It's going up, 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 up. Area is increasing. Then what happens to the signed area now? Starts going down, right? And somewhere here it was 0, and now it's getting more negative. All right, so somebody new. What's the relationship then? How can I write a relationship between P and Q? Did anybody get this? Is it Oren? Oren, tell me. This is what he said. See if you agree. Do you agree with that? Q of X is the integral from 1 to X, P of T dt. Perfect, right? Because P is the rate of change of Q. We're accumulating, we want the variation in signed area starting from 1, right? And P is the rate of change of Q, which is our signed area. Are we good? Okay, so a little bit, another one of these. Good practice, so you know what's going on. So now I've got P and F, which are the same. But I've got two new ones. I've got G and I've got H, okay? So I want you to figure out what G is, figure out what H is, and then again, write relationships with G and with H. So now I'm giving you two questions, okay? Figure out what G is, write a relationship for G. Figure out what H is, write a relationship for H. Go. Total negative area. Okay, so let's see, is it a signed area or an unsigned area? Let's ask that. Would G be a signed area or an unsigned area? It's a signed area, okay? So is it the same as the function q? If I were to write its assigned area, do I just write the same thing as q? How would I set up the accumulation of signed area according to what it's showing for G? Yes, sir? He wants to start at 2. So what happens? If you start accumulating at 2, signed area, what's it going to be immediately? Negative. That's what's happening, right? So I'm not showing you anything until 2. And then as soon as you start accumulating the signed area, it starts getting negative and more negative. You're accumulating the opposite of the gray area, right? The opposite of the gray area. So can I do P of t here? Or F of t, right? P of t or F of t, the same thing. Okay, how about H? So what do you see with H? Somebody new? Anyone think they got what H is about? Yes, sir? Total unsigned area. What do you think? It starts the same way that what Q did, but then when you get to 2, it keeps adding area. Okay, so how am I going to write that function? So it's still starting at 1. How am I going to get unsigned area? I want to get this to be a totally increasing area no matter what. So who was telling me? Yes? What will it be? How will I do that? How can I do that? Because if I put F or P, it's going to go down whenever that's negative. So how can I make it always increase? Lots of hands here. Absolute value. Is that what you all were going to say? What does that do? It takes whenever P is negative, it's going to make it positive. And so then what will happen? We'll increase at a positive rate. And that area will just keep going up and up and up. And we'll truly get the area. Right? We'll truly get the area or unsigned area. So in recitation this week, what you're going to do is I want you to rewrite h of x without absolute value. You guys will work on that. So without, because this is kind of the cheater way of doing it. This is kind of cheating, okay? So can we create that function without absolute value? So that is a good test of all this stuff we're talking about. And so you'll work on that in recitation. Any questions? Please. So whenever at the beginning here, when the function is positive, it has no effect, right? But then when this turns negative, like past 2, it'll instead of the rate being like this, the rate will be like this, and it'll just add up all that area because it's that rate will be negative. It'll just keep adding more area. Because at like this positive rate, that's the mirror image of that one. Does it make sense? It makes everything positive, whether it was already positive or whether it was negative, turns it positive. Therefore, you're going to always get a positive rate, and you're just going to keep adding area, even if it's below. Does that help? Cool. All right. So we're finished with talking about area and unsigned area. So if you have started the iMath AS, then hopefully any confusion that you had will be cleared up because you have all the language and all the concepts now to do the iMath AS, which I think is at Wednesday at midnight. Okay, so you got plenty of time to work on that. Get started early. So next we're going to talk about volume. If I want to create a volume accumulation function, what do I need? If I want a volume accumulation function, what's the key thing I'm going to need to write a volume accumulation function? The rate of change of volume, right? We've got our template, we've got our integral, net accumulation function that works for any quantity, and all we need is the rate of change of that quantity, and we can set up the integral function, and we've got our net accumulation function. So let's talk about how we're going to do that with volume. So what we're going to do is here's how this is going to work. Most problems. Okay, so there's other ways of creating volumes, but here's a common way, and that is to take a function. So this is sine of x from 0 to pi. This is sine of x from 0 to pi. Okay, so x-axis, y-axis. And so what I'm going to do is I'm going to take that curve and I'm going to rotate it around the x-axis, and it's going to create like an empty shell. What will that look like when I'm done? What kind of thing would that look like? Around the x-axis. Around the x-axis. What kind of... Someone said a football, right? It's Super Bowl season, right? If I rotate that thing around the x-axis, that's going to create Can you imagine that if you like let those points, if you imagine all the points that are being touched in space by that as you rotate it around, like if it leaves a trail, right? If that black curve leaves a trail as it goes, can you imagine what you would get? You're gonna get an empty shell that's kind of like a football. Do you see that? So then what we're gonna do is we're gonna fill that shell up bit by bit, and we're gonna track the accumulation of volume as we fill it up. And so then if you want the whole volume of that thing, we're gonna take the value of the function at the ending value, right? So the first thing we're gonna do is we're gonna create an empty shell. We're going to create an empty shell, and then we're going to track the accumulation of volume as we fill up that shell. And so then we'll have a volume accumulation function, and if we want the whole volume, then we'll just take the value of the function at the end, and that'll give us the volume of the whole thing. Does it make sense? So I could also rotate that about the y-axis. And can you imagine, will you get the same kind of shape if you rotate around the y-axis? Totally different. So if I rotate around the y-axis, am I going to get a football this time? If I think about all the points that are swept out in space, what am I going to get when I do that? Shoot, I pushed it too early. Here we go. Kind of a donut, but not really a donut. You guys know what a bundt cake is? Or are those out? Or those old school? Yeah, so it's like kind of like a bundt cake. Same thing, but I've started totally different. So I'm getting a totally different shell to start with. But what we're going to do is we're going to create this shell, and then we're going to fill it up. And as we fill it, we're going to accumulate the volume filled. We're going to keep track of how much volume has been filled so far, and that's a volume accumulation function. And then if we want the whole volume, then we just use the function and evaluate it at what? At x equals pi. So the question is, what are we going to fill these up with? So what we're going to fill these shells up with is what's called right cylinders. Okay, so this is a right cylinder, and as we're filling up these shells, these cylinders are going to be growing in one of two ways in the current interval. In the current interval, the shells are either going to be growing in height, up like that, or the shells are going to be growing in radius, out like that. So remember we make intervals. We're going to have cylinders, okay? And so we're going to have cylinders growing in the current interval in one of two ways. Either at the left, they're going to grow in height, or those cylinders are going to grow like the right hand one in radius. And so what we need is the rate of change is going to be determined by how these cylinders grow. So the rate of change function that we need to get the volume accumulation function is going to be determined by if that shell's growing in height, we're going to get a certain rate of change function. If those shells are growing in radius, we're going to get a different rate of change function. So that's what we got to figure out next. What is the rate of change when the cylinders grow in height versus when they grow in radius?